Sounds pretty simple on the surface, but it really opens up, well, a whole universe of complexity and beauty.
It does indeed.
The question is a particle's frequency, in fact, its momentum?
It's a great question. Really insightful.
Right. It hints at this connection, but maybe not a direct one-to-one thing, more like a subtle interdependence.
Exactly. It forces us to look at the foundations, quantum mechanics, special relativity.
And how they weave together. So our mission today is to deconstruct this relationship for you. We want to build a more accurate, kind of nuanced picture.
And we'll see right away there's a key distinction. Momentum isn't just any frequency.
Right. It's linked to spatial frequency, like how the wave oscillates in space.
And total energy, that's tied to temporal frequency, how it oscillates in time.
Does that initial distinction resonate with you as you first hear it? Keep that in mind as we go.
Definitely something to hold on to.
So how did physicists even get here? This idea of duality, that things can be both wave and particle. It's pretty weird.
It is weird, and it wasn't, some philosophical preference. It was forced on them by the experiments. Hard data.
Data that just didn't fit the old models.
Right, and what's fascinating is how it happened differently for light and matter. Light, everyone knew was a wave.
For centuries, yeah. Huygens, Maxwell.
Exactly. But then experiments around the turn of the 20th century reluctantly pushed it towards being particle-like too.
And electrons.
The opposite. Firmly particles, right. But then they found undeniable wave behavior. It just shows our classical boxes are too small.
Okay, let's start with light then. That classical wave picture was dominant for so long.
It really was.
But then came these experiments starting around 1900 that just, well, broke the mold.
They were completely baffling from a classical standpoint.
The big one, the one everyone learns about, is the photoelectric effect.
Ah, yes.
Classically, you'd think brighter light means more energy, so it should always knock electrons out of metal, maybe give them more kick.
That's the intuitive classical prediction. More intensity, more energy transfer.
But the experiments, like Lenard's, showed something totally different. First, there was this minimum frequency.
A threshold frequency, yeah. Below that, nothing happened. Didn't matter how bright the light was.
0 electrons. And then the energy of the electrons that did come out
depended only on the light's frequency. Not the intensity, not the brightness. Higher frequency, higher energy electrons.
And more brightness just meant more electrons, not faster ones.
Right. And the emission was instantaneous. No delay for energy to build up, which classical waves would need.
Total puzzle. Until Einstein stepped in.
1905. His explanation was revolutionary. He said, look, light energy isn't a continuous wave. It comes in packets. Quanta, later called photons.
And he linked the energy of each packet directly to frequency. E equals HF.
Exactly. E is energy, F is temporal frequency, and H is Planck's constant, this tiny but crucial number connecting the quantum world to ours.
So 1 photon in, 1 electron out, if the photon has enough energy.
Precisely. It needs enough energy, HFE, to overcome the metal's binding energy, the work function. Any extra becomes the electron's kinetic energy. It explained everything perfectly.
Wow. So light is particles in some sense. But that was about energy. What about momentum?
Good question. That came a bit later with the Compton effect around 1923. This was maybe even more definitive proof of the particle nature because it showed photons carry momentum.
Which is like the definition of a particle property, right? Something having momentum.
Pretty much. Arthur Compton shot high-frequency X-rays at electrons.
Okay.
And he found the X-rays that scattered off came out with a longer wavelength.
Longer wavelength means lower frequency, lower energy.
Exactly. The X-rays lost energy in the collision. And how much they lost depended on the scattering angle.
How could a wave do that?
It couldn't. Not according to classical wave theory. Compton showed it worked perfectly if you treated it like a billiard ball collision. An incoming photon particle hitting a stationary electron particle.
A relativistic collision, even.
Yes, relativistic. And crucially, he had to assign momentum to the photon. And the value he needed, PEC or PZ, fit the data beautifully.
So Compton's scattering nailed it. Light acts like particles carrying both energy and momentum.
Undeniable evidence. The wave-only view was officially dead. Duality was taking shape.
Okay, so light, a wave, can act like a particle. This naturally leads to the question, could particles act like waves? Symmetry suggests maybe.
And that's exactly what Louis de Broglie proposed in his PhD thesis in 1924. A truly bold idea.
He just flipped the script?
Pretty much. He hypothesized that the relationship between momentum and wavelength seen in photons, PIA, should be universal. It should apply to matter too.
So O equals H divided by P for an electron for anything.
Yes. A direct link between momentum a particle property, and wavelength, a wave property. He imagined particles having associated matter waves.
That's elegant, but purely theoretical at first.
Completely speculative,
Right.
brilliant, but needing proof.
And the proof came.
It did, just a few years later, 1927. Two key experiments, independently confirming electron diffraction, which is a classic wave phenomenon.
Let's hear about them.
Okay, first, the Davis and Germer experiment at Bell Labs. They were actually just studying how electrons scatter off nickel. Routine stuff.
Until
An accident. A vacuum tube cracked. The nickel target oxidized. To clean it, they heated it really strongly.
And that did something unexpected.
It annealed the nickel, basically turning it into large, regular crystals. When they started the experiment again, boom. Instead of a smooth scatter, they saw distinct peaks. Electrons were bouncing off at specific angles much more often.
Like light diffracting through a crystal.
Exactly. Davison realized the crystal lattice was acting as a diffraction grating for the electron waves. The peaks were constructive interference.
Wow, and did the numbers match de Broglie's idea?
Perfectly. They calculated the expected electron wavelength using Abe, based on the electron's energy, and it matched the angles needed for diffraction by the nickel lattice. First direct proof.
Amazing. And the second experiment?
At the same time, independently, G.P. Thomson in Scotland.
Wait, Thomson. Like J.J. Thomson, who discovered the electron particle?
His son, George Paget Thomson. He fired high-energy electrons through a very thin metal foil, a polycrystalline one.
So lots of tiny crystals, randomly oriented.
Right, and what he got on his detector plate was concentric rings.
Like an X-ray diffraction pattern.
Identical, unambiguous visual proof of electron diffraction. And crucially, he also showed that if you increase the electron energy,
Higher momentum.
their de Broglie wavelength got shorter and the rings got smaller, exactly as Hubble predicts.
So double confirmation. Particles definitely have wave nature.
No doubt about it. It's funny, though, that historical path. Light as a wave, grudgingly accepted as a particle. Electrons as particles accidentally discovered to be waves.
Yeah, it shows how ingrained the classical ideas were. So the big takeaway here, what does this duality mean?
It means our labels, wave and particle, are just incomplete. They're projections of a deeper quantum reality that doesn't fit neatly into those boxes. Our language struggles.
Okay, so experiments forced this dual picture. Now, how do physicists actually talk about this mathematically? How does the language of quantum mechanics handle it?
That's where we get back to our initial distinction. The math clearly separates temporal and spatial frequency.
Right. Energy goes with one, momentum with the other. Let's break that down.
So first, energy. We have the Planck-Einstein relation. We saw the photoelectric effect, EF.
Energy equals Planck's constant times temporal frequency.
Exactly. Or often in quantum mechanics, we use angular frequency, omega, which is just 2 times F. So you write EOD, A car, HR, it's just H divided by 2.
Just a different unit for frequency, basically.
Right. But the core idea is energy is proportional to temporal frequency. How fast the quantum state oscillates in time. Higher energy, faster oscillation, like its internal clock speed.
Okay, energy is temporal frequency. What about momentum?
That's the de Broglie relation. We usually see Yutar-Kimiti, but let's flip it and think about spatial frequency.
Instead of wavelength, how many waves fit in a certain space?
Exactly. We call it the wave number K. It's 2 divided by the wavelength. So K represents spatial frequency.
Okay.
If you rearrange de Broglie's relation to P and substitute K, you get a beautifully symmetric equation, P ache.
Ah, so momentum is proportional to Planck's constant time spatial frequency.
Right. Precisely. Momentum dictates how rapidly the wave function's phase changes as you move through space. Higher momentum means more compressed waves, a shorter wavelength, a higher spatial frequency.
So E key energy time and P momentum space, a clear division.
A very clear division. Temporal frequency for energy, spatial frequency for momentum.
And what's the thing doing the oscillating? What connects these?
That's the wave function, often written as psi. It's the central object in non-relativistic quantum mechanics.
The probability map you mentioned?
Sort of. Its magnitude squared gives you probability density, but the function itself is complex. It has phase, and it contains all the information we can have about the system.
And it oscillates both in time and space.
Exactly. For a simple free particle, it looks like a plane waves, and its phase has 2 parts. One part evolving in space, governed by K, and thus momentum, and another evolving in time, governed by O, and thus energy. It unifies everything.
Okay, this separation, P ache, that sounds like it might connect to something else fundamental and, weird about quantum mechanics, the uncertainty principle.
Absolutely. It's the direct origin of it. The Heisenberg uncertainty principle isn't some fuzzy limit on measurement. It's baked into the wave nature itself.
How so? Because momentum is spatial frequency.
Precisely. Think about any wave. If you want to know its frequency very precisely, the wave needs to extend over a large region, ideally infinitely. A pure single frequency is spread out.
Okay. Like a pure musical note needs time to establish itself.
Good analogy. Conversely, if you want to localize a wave, like a very short blip or pulse.
It can't be a single frequency. It's made of many frequencies combined.
Exactly. There's an inherent trade-off. Better localization means a wider spread of frequencies. In quantum mechanics, position is localization in space, and momentum is spatial frequency. P, so Hebb, is related to Wick.
So if you want to know the position accurately, small px, you need a wave packet made of many spatial frequencies, large px.
Which means a large uncertainty in momentum, large, the math works out to x times key, must be greater than or equal to divided by 2.
The Heisenberg uncertainty principle derived directly from px.
It's a fundamental consequence of identifying momentum with spatial frequency, not about measurement limits, but about the nature of matter waves.
Mind-bending. Okay, so we have the quantum language, EOP here, but you mentioned earlier this isn't the whole story without relativity.
Correct. These quantum relations give us the vocabulary, but special relativity provides the essential grammar, especially when things move fast or have no mass.
How does relativity change the picture for energy and momentum?
Well, classical PMV just doesn't work at high speeds. Relativity tells us momentum increases non-linearly as you approach the speed of light, needing that Lorentz factor, gamma.
Right. Doggle 1 over the square root of 1 minus v squared over c squared.
That's the one. So relativistic momentum is P2, and total relativistic energy is E equals Cpo, where m here is the rest mass, the invariant mass.
Mass something has when it's not moving.
Exactly. And the concept of relativistic mass increasing with speed is kind of outdated now. We prefer to think of rest mass as invariant and momentum energy changing.
Okay, but those still depend on velocity, on gamma. Is there a more fundamental link between energy, momentum, and mass?
There is, and it's one of the most important equations in physics, the relativistic energy-momentum relation. E squared equals pc squared plus m euros squared.
Pc plus me squared.
That looks significant. It is. It connects total energy, E, momentum P, and rest mass, m, without involving velocity directly. It's true in all inertial frames, a real cornerstone.
And you said this works for everything, massless particles too.
That's the beauty of it. Let's test it. What if a particle is massless, like a photon? What's m?
0.
Right, so plug in m0. The equation becomes E, PCC.
Or just EPC.
Exactly. Energy equals momentum times the speed of light. This shows a massless particle must have momentum if it have energy. It's not an option, it's required.
Which fits perfectly with the Compton effect needing photon momentum, PEC.
Perfectly. And it implies massless particles must travel at speed c. Now, what about a massive particle at rest?
At rest, momentum P is 0.
So the PC term vanishes. We get E pelego excess MSECNE.
Which means E pesetameno, Einstein's famous equation.
But specifically for the rest energy, the energy something has just by having mass. So this single relativistic relation covers both extremes.
That's incredibly powerful. So how does this relativistic equation connect back to the quantum frequencies, Ben-Aimé?
Now we truly unify things. We take the quantum relations, Iodo and P, and plug them directly into the relativistic EPC plus mu scope.
Okay, so A equals A plus mu.
Precisely. This equation links the temporal frequency and the spatial frequency K for any free quantum particle constrained by its rest mass, MOO, and the fundamental constants at and C.
That feels like a really deep connection.
It is. It's called the relativistic dispersion relation. It tells you how the time oscillation rate must relate to the space oscillation rate for a matter wave, dictated by its mass and the rules of relativity. You can't fully describe wave-particle duality without bringing quantum mechanics and special relativity together.
Wow. Okay, so let's synthesize. We've got the quantum links, E to OPT, and the relativistic framework plus MEO A to AT. We're finally ready to tackle the original question. Is frequency momentum?
Yes. And now we can see the answer is nuanced. The key is realizing a massive particle actually has two important frequencies associated with it.
Two frequencies? Okay, What are they?
First, there's an intrinsic one, tied purely to its mass. Remember, E arrow, M arrow, O, the rest energy.
Yeah, energy just from existing.
Apply EHF to that rest energy. You get a frequency, FC equals M euro ACH. This is called the Compton frequency.
So it's the frequency equivalent of the rest mass energy.
Exactly. It's fundamental, intrinsic to the particle, doesn't depend on motion. Think of it as the baseline internal ticking rate set by its mass. Zero momentum, but still has this frequency.
Okay, an intrinsic Compton frequency from mass. What's the second one?
The second one depends on motion. When the particle moves, its total energy E is greater than its rest energy E air. Its E equals gem year air.
Right, includes kinetic energy.
So the frequency associated with this total energy, FdB equals HEH, FDH ERH, is called the de Broglie frequency.
Ah, so it's like the Compton frequency boosted by that relativistic gamma factor.
Precisely, FdB times Fc. Since gamma is always 1 or more, the de Broglie frequency is always greater than or equal to the Compton frequency. It depends on the particle's speed relative to you.
So it represents the total oscillation rate, including the part from motion.
Yes, the combined oscillation from its existence, mass, and its movement, kinetic energy.
Okay, two frequencies. Compton, intrinsic from mass, and de Broglie, total, includes motion. How does this answer is frequency momentum?
It clarifies why the answer is no, but also why the intuition behind the question is understandable. Fundamentally, momentum P is proportional to spatial frequency, key K. Total energy E is proportional to temporal frequency, or F, E. They're different things tied to different aspects of the wave.
So strictly speaking, frequency is not momentum.
Correct, but there's a causal link.
Ah, the connection we sensed at the start.
Yes, think about the chain. 1, momentum means motion. 2, motion means kinetic energy. 3, kinetic energy adds to rest energy to give total energy E. 4, total energy E determines the overall temporal frequency, the de Broglie frequency, FdB.
So momentum causes the temporal frequency to increase above the baseline Compton frequency.
Exactly. Momentum leads to higher total energy, which manifests as a higher de Broglie frequency.
Okay, let's revisit that initial thought. A particle must have momentum to have a frequency. How does that hold up now?
It depends which frequency. It's wrong for the Compton frequency that exists even with zero momentum, just due to mass.
Right.
But it's correct if you mean the de Broglie frequency needs to be higher than the Compton frequency. To get that extra frequency boost, you must have momentum to provide the kinetic energy.
So momentum is needed for the increase in temporal frequency above the rest mass level.
That's the precise relationship.
And does this frequency duality have a parallel in wavelength?
It does, and it's quite revealing. There's the Compton wavelength, like Inc AEC, which is a fundamental length scale related to the particle's mass.
Okay.
And then there's the de Broglie wavelength, what it B equals HAC, which depends on momentum.
How do they behave differently?
As velocity increases from 0, the de Broglie wavelength decreases from infinity. The wave gets more compact. The Compton wavelength sets a kind of fundamental scale. It shows a neat symmetry. At rest, PD, sharp momentum, but TB is infinite, totally delocalized waves. As it gains momentum, ED shrinks, the wave becomes more localized, allowing things like diffraction.
Very cool. Okay, so to sum up this deep dive, the simple question is frequency and momentum leads us to a much richer picture.
Definitely.
Frequency is not momentum. Energy E is tied to temporal frequency via EO. Momentum P is tied to spatial frequency via PP. Clear separation.
But the intuitive link is real. It's causal. Momentum gives kinetic energy, raising total energy, which in turn raises the overall temporal frequency, the de Broglie frequency, above the baseline set by mass, the Compton
So
frequency.
you need momentum for that extra frequency due to motion.
Precisely.
And thinking bigger picture. This whole wave-particle duality thing, trying to force quantum objects into classical boxes, maybe that's the real issue.
I think so. It's historically important, helps us learn, but ultimately it reflects the limits of our intuition and language.
So what's the modern, more complete view?
That comes from quantum field theory, QFT. It offers a more unified perspective.
How does QFT resolve the wave-particle thing?
In QFT, the fundamental things aren't particles or waves in the classical sense. They're quantum fields permeating all of space-time.
Fields for everything, like an electron field, a photon field.
Exactly. And what we perceive as a particle, say an electron, is just a localized, quantized excitation like a ripple or vibration in the electron field.
Ah, so the particle is an excitation of the field.
Yes. And what we perceive as a wave is more like the collective propagating behavior of these excitations in the field.
So wave and particle aren't two separate modes it switches between?
No, they're just two different ways the underlying quantum field manifests itself, depending on how we interact with it or observe it. QFT subsumes both concepts into this deeper field structure. No paradox.
That feels profound. It removes the
Uh,
dichotomy. But it also highlights how hard it is to grasp this stuff using everyday concepts.
Absolutely. It's at the heart of why quantum mechanics often feels so counterintuitive and leads to ongoing philosophical discussion. Our language evolved to describe chairs and trees, not quantum fields.
So the QFT view offers this different reality. Thinking about that, what stands out to you as the biggest way our everyday language or intuition might actually hold us back from understanding the universe at its deepest levels?